Welcome to this penultimate installment of our O-REU seminar series. Today we have a talk from Bradley Jared, currently at Sandia, soon to be at Tennessee, on addressing complexity in additive manufacturing. Bradley, please take it away.
Thank you very much. Appreciate it. So I'm in the last days of my time here at Sandia, about to start at the University of Tennessee. So I'm going to talk about the work we've been doing here at Sandia. So I'm going to give a brief overview. I believe I got 45 minutes here. Talk a little bit about additive manufacturing and what we've been doing here at Sandia. This is work I've been involved with. There'll be a lot of work I won't talk about because there's a lot of activity. But I want to address some of the issues that we've been looking at. So we're going to talk a little bit about this idea of complexity. If you have been in additive manufacturing, or maybe follow additive manufacturing, or maybe are new, a lot of people get excited about some of the things that we're doing in additive manufacturing. A lot of it stems in this idea of complexity, right? So geometric complexity is generally the concept that's being discussed, but it has a lot of different tentacles that reach out in different areas. I'm going to talk about some of those. And really it becomes a real problem and a real challenge, right? And so I think that's going to be obvious. So a little bit of this, concept, there's lots of things we can do in the additive space that are new and different and exciting and interesting in research and development. Here at Sandia, we've been doing a lot of work, looking at advanced manufacturing techniques, not just additive, but in here I'll talk about additive, in terms of giving us design tools that allow us to do our mission space here at Sandia. So a lot of our work is mission critical, high consequence types of hardwares for security systems. Familiar with some of the work that we do at Sandia. The other labs are obviously involved, have some similar mission spaces. We overlap and collaborate in a number of areas. But you see here a lot of things, some examples of parts that I can show you on things that we're doing. On the bottom left is actually a mirror assembly that we generated almost 3 years ago, where we actually did a flexure mount for a mirror assembly and then diamond turn that. So we've got on the top surface and mirror surface and optical image capability, and we've got the internal mechanisms, right? So that's a part you can't do any other way. The top part, top right, is a part we actually shot in a hot shot or a sounding rocket that shoots off from Hawaii Test Facility in Hawaii. This was done, I believe, let's say a year ago. That's actually a part on the top right. You'll see that maybe a couple other places, but that's a part that we printed in our lab. We actually had a 1,000-pound load capacity for that part, and actually they did a load test and didn't fail at about 18,500 pounds. So they actually flew that part in the rocket. So that was a mounting point for assembly, and a fairly complicated part we did with topology optimization. You see some support structures and stuff like that, but it gives us a new capability to design parts in a different way. And then the bottom right is actually some work that I've been doing recently. We'll talk about this a whole lot, but basically we've been looking at dynamic impact. So this is actually a part that we shot at a gas gun at Los Alamos in collaboration with them and Lawrence Livermore on a project where we hit this at about quarter of a kilometer a second. And so we've been doing work looking at simulations and impacts and the dynamic properties and all these sorts of things, right? So these are all examples of complex geometries that are really compelling and of interest to Sandia because they give us the ability to sort of address our mission space in a new way. And do some things that are kind of exciting and fun. Let's see. So I'll talk real quickly a little bit about some of the work we actually do at Sandia, so give you a flavor in the additive space. I don't know if anybody's talked about this. I don't think so. I'll talk first about some of the lens process. So this is actually a process that came out of Sandia in the mid-90s. Lens is engineered net shaping, also called directed energy deposition by a lot of people. This is a powder blend process where you basically have powder flows, and where it converges with a laser focus, you get a melt pool and you deposit material. This is actually a custom machine we have in our lab where we can do multi-materials. You can see some things there. There's a lot of work we're doing right now with high entropy alloys, the new alloy system. So this system is very flexible. It's open. We have control of all aspects of the hardware and the software. And so that gives us a lot of unique capabilities for process monitoring and stuff like that. We also have a sister facility in California that has a similar machine that's a commercial available counterpart to this. Another area where we're doing a lot of work is looking at wire feed deposition. So again, sort of a DED process. So now we're using wire instead of powder for a number of reasons. One is safety, right? Wire is not explosive. Powder and many of these materials, particularly reactive alloys like aluminum and titanium, are explosive and have a lot of safety risk. But it also allows us to scale up and generate much larger parts. And this is a growing area here at Sandia and other places of large parts for large applications. And so again, think about these, and a lot of times these are maybe not a net shape part, but it's a near net shape part that still requires a lot of machining. But we've been doing a lot of work here with a range of welding technologies. And this is actually some work I'll be doing when I go to UT. But you see the capabilities as an example there of work we've been looking at, right? And so some simple geometries, materials look really, really nice, and we're trying to understand those sorts of things. Another area where we do a lot of work here at Sandia in the additive space is in the direct write space. So this is actually, you'll see the context there in the bottom, Adam Cook and Brian Kerr. And so these are not necessarily metals. Usually they're not metals, although we can do printed metals with nano inks. There's a range of processes we have here. A lot of these are depositions or jetting processes, maybe extrusion casting. And you can see there's a wide range of materials that are available there on a wide range of substrates. And so at Sandia, we sort of cover the entire gamut of this process, from formulation of the inks and the materials and the paste and the feedstocks to synthesizing those elements, to characterization, and then finally to printing and curing and sintering and all the things that are involved. So we kind of cover the entire process chain in this space, and we've done things from printed circuit board types of things. You see at the top, you can put formal prints. We've actually printed battery structures and actually tested those and done cyclic loading on those. There's quite a bit of work looking at compression pads. You can see the pad on the side there, the sort of silicone-based geometry. We looked at different traces and inks and materials that can even cure at, say, room temperature. We've also done quite a bit of work in the ceramic space. So these are all areas of growing research interest, and a lot of work where we've done that really impact our mission. And so really exciting capabilities in this space, different from what I'm going to talk about, but again, some of the same problems apply. An area that's really unique with Sandia and actually the other national labs, Lawrence and also Los Alamos, is our interest in energetic materials for our mission space. So we've actually done quite a bit of material. This slide is quite just happened and others have done. Some of this goes back almost a decade or more. And so this is work where we're looking at depositing energetic materials for a number of reasons. Some of it's safety, some of it's performance, but these are all materials that are typically using sort of a direct ink write process we saw on the previous slide. But it's all work that we're doing at Sandia to really understand, and this is actually a growing area for us for a number of applications. But it's very distinct and it's sort of unique too. You're not going to see a ton of energetic materials in the additive literature, although that's growing. The process I'm going to be working on and talking to you primarily this morning is laser powder bed fusion. So this is a very popular metal technique. The machine in our lab where almost all these parts have been made is a ProX 200 by 3D Systems. It's a continuous wave ytterbium single mode fiber laser. We run at about a micron wavelength. Max power is at 300 watts. We typically run about 100 to 110, and then we have about 100 micron spot size, right? So in this process, you put down a 30 micron layer of powder. You see on the bottom right, you see the geometry or the video of the actual machine running. Then we scan a laser at a high speed. So this is about 1.5 meters per second that this thing's scanning. So we get extremely high cooling rates. You get reasonable deposition rates with this. It's actually relatively slow, 100 cubic meters per minute. I think it's supposed to be an hour actually, so that's a little bit fast, but 100 cubic millimeters per hour is fairly slow, but it's reasonable. Like, we've built lots of parts with these. And a lot of times this is a turnkey system, so we run it overnight and do a lot of things like that. So we're typically doing all of our work in stainless steel, and you can see some of the parts up there. There's high throughput dog-bone samples. You'll see those again in a minute. A lot of the work we're doing to characterize material properties and those sorts of things. And then there's a cool sort of a bling part we got there with Sandia T-Bird, where we put a lattice structure in there. That's just kind of a cool part to give away to people and that sort of thing. Again, there's lots of complexity available. Again, we think about it oftentimes in terms of geometric complexity, but there's also things you can do in material complexity, particularly with things like direct write and some of the new processes that are combining hybrid and multi-materials and all that sort of stuff. But one of the things, particularly when you think about a high consequence application space where we work at Sandia, is that every time you have some sort of a feature, and so complexity introduces features, right? So if you have a cube, you've got a fairly simple geometry. Now, if you go to a lattice, that's extremely complicated. So every one of those struts or nodes can be considered a feature. And if you think about trying to qualify or certify or verify that those parts are actually meeting requirements, now suddenly you have to think about how do you inspect them, how do you verify them, how do you validate them. that comes from a development cycle. It comes from a production cycle. All these things become things you have to pay for, right? And so complexity isn't free. Sometimes people want to say complexity is free. In our space, that certainly is not the case. Complexity may be free from a process standpoint, but from a validation and actually end use, there's a lot of complexity we still have to pay for. And again, AM brings sort of a new paradigm that we've been working on here for the last 3 or 4 or 5 years. That's somewhat new to us. A lot of people that do things like castings have dealt with this for a while, where you basically are generating your part and your material at the same time. Additive still brings a different local behavior that's unique to, say, casting. But really, the key piece for us in our business is, when do we have a bad part? So if we're going to put something in a weapon system or a security system, we need to know if it's not going to work, right? We assume things work, and we have to be able to verify and validate, throw out bad parts, right? So we're not necessarily profit driven, but we've got to execute on our mission. And so this brings in a lot of things. And so you can see on the bottom right there, sort of a float diagram or circle diagram that we generated that shows, when we think about all the things that require us to create good parts, we start with whatever our design requirements are. And then in the additive space, we start combining geometry, material, and the process, and these all converge and meet together, right? The geometry is based on the material, but it's also connected to the process and all these sorts of things. And these sort of feed into this sort of, control the process. We validate the process, we inspect the process, so ultimately we get a part that we can accept, qualify, to certify the terms that people use, right? So we have to understand, these materials. We have to understand these processes. We have to understand what the geometries actually are, right? So we have to characterize all these things. And a lot of the work we've been doing is understanding this complexity, particularly in the material science space, right? To understand how we're going to actually qualify these types of parts for our application space. So this is sort of providing a scientific basis for this, right? And so to that end, a lot of the work we've been doing, you'll see this, it's been focused on trying to understand critical defects and also the concept of signatures in the process, or even the part itself, that are useful to identify where those critical defects are. And so we see that in terms of process monitoring. We see that in the modeling space. We see that in the validation space, or inspection, and those sorts of things. So one of the ways we've been tackling this problem at Sandia is, this is actually a program that's been completed a couple of years ago, but it was a large research project called Born Qualified, and there's a title you see, Changing the Engineering Design Qualification Paradigm, sort of a philosophical comment. But really, this somewhat busy chart shows you all these elements we're trying to pull together, and I want to talk to several pieces of this, but this is sort of at Sandia is how we thought about it. We have the process, we have the parts, we think about trying to make measurements, we try to develop and understand and characterize the properties, we develop models, and then we do predictions, and we sort of put all this stuff in a feedback loop, and then we come back to something that's refined, and it's going to be requirements, right? So there's all these elements in the work we've been doing. I'm primarily talking about the process space. It's a little bit in the measurement space and in the property space. I won't talk much about the models, although the next slide talks a little bit about the work that we are doing at Sandia. This is not my work. This is lots of other people, and you can see them listed here. So there's interest in this space. You can reach out to myself or somebody at Sandia and get you connected with the right people. But lots of work across all the scales. So this is for laser powder bed fusion. We have things go from the powder scale. This is actually DFT and molecular dynamics, all the way up to part scale, where we're looking at residual stresses and deformations and all scales in between, microstructures and those sorts of things. So there's a lot of things going on here, and we've been working. It's a multi-scale, multi-dimensional, multi-temporal scale type problem that we've been working on. So a lot of different pieces of this. So, and a lot of the work you'll see is kind of feeding into some of that. So one of the things we learned very quickly was, with a lot of this complexity, we can actually generate parts very, very, very quickly. And one of the things of a project I was leading early on, so 4 or 5 years ago, was the fact that we have the ability to create material very quickly, but we have to characterize it just as quickly to stay on top of the game. And so this was some original work for a high throughput tensile tester, because this is sort of where we started with trying to validate materials. And we're using direct digital image correlation, DIC. You can see the bottom right animation of the actual real-time image pulling. And it gives us stress strain curves, right? And so what we start off with is sort of the concept at the bottom, where we have these, we call it a cooling fin, because it's kind of what they look like a little bit. These dog bones, we cut these off with a wire EDM, and then we can load these into the drop-in tensile testers you see at the top right. So one of the things that was nice about this is it sort of changed the paradigm in our lab about how we are doing tensile testing. So typically we use extensometers and things like that, fairly delicate, or at least intensive setups. And so, a lot of times you'll get, I don't know, maybe 10 samples a day sort of thing. 20 if you've got a technician that's fantastic and does a really good job. This actually allows us to do samples that are sort of dropped in with some custom grips on a load frame, able to do these, 10 an hour maybe or more. And we've actually been able to demonstrate the more like one every minute or so, right? So this really changes the ability to capture large data sets. And this is important because one of the things we've learned as we started looking at these materials is, people ask lots of questions about whether additive materials is, as good as rod or whatever. My answer is always it's different, right? So if you think about a wrought material or a casting or a forging or a heat treat or a rolled material, they all have different properties. And a lot of what we've been doing is trying to understand and quantify those materials. And so here's some early data on 17.4, which is actually a relatively poor material at this point. But the real key here is the fact that there's a very wide distribution and spread in the data of the stress strain curves of this material, right? So you can see one of the things, typically as a mechanical engineer, I often think about materials having a property, right? It's got a modulus or a yield strength or an ultimate tensile strength or whatever. And it's always true, but in additive, we have these things like defects and surface finishes and microstructure variations. And what happens is we have a much larger spread in the material data. I have some data, I don't think I have it here, where a wrought curve, pretty close on top of each other, right? And so we start thinking about how do we have distributions. We've done work with Weibull distributions, which are very common in even the casting industry and also ceramics, where you start thinking about, well, if I get enough samples, I can sort of establish some sort of a probability threshold at which this material can perform. And so now that can inform how you make decisions in terms of design, right? And so again, part of the question is how do we get this data quickly and fast? And that's what a lot of the work we've been doing. But this is, again, quite a bit of uncertainty. If you look at the wrought material here, the strain to failure range is maybe 1%, and we've got almost an order of magnitude higher than that here, right? So there's a challenge there. So a lot of the work we've been doing over the past few years has actually been trying to take understanding material structures and tying that to the properties themselves. There's a modeling aspect of this. There's an inspection aspect of this. We've done a ton of work with micro CT, which is becoming a sort of an industry standard in terms of inspection for additive parts, right? It's got limitations, but it's got a lot of ability as well. And so we did a lot of work here early on trying to understand porosity fields and largest defect size and these sorts of things. And you see some stuff we've got over there on a publication that showed all the different porosity metrics you can come up with and what those look like, right? There's a number of them. And so the question is, what's important? What matters, right? And so this slide's going to be a little bit of a worst case. The next slide's going to be a little more encouraging. This slide shows sort of a worst case. We have two different dog bones, the left one, the right one, A and B, or B and C, I guess it is. And, we look at those porosity fields and we think, the one on the right, C, is going to have a much lower strength and much lower strain of failure because there's a larger porosity field. It has a lot more defects in it. You would expect a large difference in the performance. But when you overlay the stress strain curves, they're right on top of each other, right? And so there's sort of two sides of this. One is encouraging in that you can sort of say, well, okay, these defects matter, but how much do they matter? And maybe these materials can be more robust than we thought. The other side of that is, okay, well, now how do I actually predict which one's good or bad? Because in the previous slide, this is data from those images. You see a large spread. So how do we figure some of that out? And it turns out, what happens in this space, and this is some other work, so this is 316, the previous slide was 17.4, you really start getting into the models are really important and valuable. So Kyle Johnson's done a ton of work here at Sandia in this space with another Sandia and John Emery. And what happens is if you have large gross porosity, right? So if you look at, whoops, oh, that's not what I wanted to do. Apologies, the wrong slide. If you look at that slide I showed a second ago, these, it's kind of hard to say, well, there's a worse pore in here, right? It's hard to say there's a really large pore. There's sort of a pore field that's sort of uniform, right? When you see that, you start seeing behavior that looks fairly consistent in a lot of these cases. And what we found is that if we have these large pores, so this is pore size, and you see this red one, and it's right really close to where this localized necking and failure occurs in this 316 part, you can start saying something about quality. And so what we've shown is that if you have, material that has sort of a reasonable uniform porosity field, that's something you would expect, you're going to see it fit in a distribution. And really what happens is now you want to think about, well, when am I outside of that distribution? So now what you're looking for is these large defects, right? And so that helps you to think about and understand a design and qualification paradigm that will work, right? So if we can define, sort of minimum or maximum pour sizes, we can start saying, okay, how do I put tolerances on inspection or process monitoring or even design, right? These are all things we've been working on. One of the things that's really interesting in this space is the fact that these parts have a lot of surface roughness on them, and so you can actually get size effective properties, right? So people want to talk about material properties and additive components, and the reality is it gets really complicated sometimes. And so what happens is we think about sort of structural properties, right? So these are, you have to really understand the dog bones. So this is some work we did and published. I don't think there it is on the bottom, where we printed dog bones that went from let's see, I believe they were 400 microns in diameter, which is the small one on the left here, all the way up to 6.25 millimeters in cross section. And you see a very different response, right? And so we sort of figured this out fairly early on and did some follow-on work, and it showed that essentially what's happening, if you look at the finite element model here, and you can actually characterize the porosity, not on the inside, but the porosity, if you will, on the outside of the surface finish, you actually get a pretty reasonable trend here. So we attribute a lot of this size effect to the surface finish and how you have damage initiation and cracks effectively on the surface, right? And so the problem here is if I have a surface finish, it's fairly constant, right? So my process is going to have, say, a 20 micron surface finish, regardless of the size of this component. That translates to, for the 6 millimeter, really doesn't have an effect. It's really not a big deal. You can kind of think of this as bulk properties. Now, if you start talking about a 400 micron sample, now suddenly 20 microns, which is effectively, if that's RA, that's effectively peak to value of maybe 100. Now you're talking about a quarter of your part is actually now essentially a crack. It dramatically reduces the strength properties, and you see that here, right? And so we understand, and we've been using this in lattice work and other things to understand, what are the properties that we need to design for a component, right? So we start looking at minimum feature sizes and stuff like that. So this is all important. This shows a little bit of back to the process distribution. So this was some early parts we received from an external vendor, 17.4. Basically, the message here is we didn't know a whole lot about the process. We didn't know the settings. We didn't know the machine type. We didn't know the pedigree of the material. We didn't know anything about the operator. We didn't know about the settings, the build environment, they're using argon, nitrogen, those sorts of things. And this is basically 8 different tensile arrays, roughly 1,000 parts, and we see a very large variation in these, and it's very concerning, right? So you see microstructure variation, you see porosity variation, and really this was not very comforting as we looked at material uncertainty of some of these materials, and so raised a lot of questions. And I'll show a slide later that shows sort of what we've done to make improvements on this. But this is a problem, right? We don't have any control. So this is if you say a process that's not being controlled, and it's not very good. So one of the things aspects of bringing control in, so we've been doing work, this is work that Michael Hyde in our group has been doing on 316 stainless steel. So we've been monitoring the powder now in our machine. The previous slide was for parts we got from a vendor. This is now a Sandia material that we're processing and characterizing with every build. One thing we found in 316, it's fairly robust, right? So now we understand if we reuse the powder, we're getting properties, we can see some of the very minor trends. But it's really important for us to track this. So every time we build a part now, we sample powder and we capture that. And so now we know sort of how often we can reuse the powder and the reliability that will give to us. Another piece of this is actually understanding the machine system itself. This was some work we did on our ProX. And so sort of the image on the left shows some issues we had. Actually, we had a thermal lens effect. So basically what happened was our 100-watt laser, our 1070 nanometer laser was heating up the focal optic, the F theta lens in the front of the machine. And what was happening is that we were losing focus. So after about 10 seconds, essentially our process conditions were changing quite dramatically. And so we couldn't actually build material. And we figured some of this stuff out, applied some offsets, and actually this is essentially the same build. And this is without an offset change. This is with, and you can see the dramatic difference in the process itself. And so the key here is that a lot of people in the additive space buy equipment and kind of plug it in and don't really understand their material, don't really understand their machine system. And these are all things that you have to characterize. These are not necessarily difficult things to do for the most part, but these are critical to getting a process that's going to be in control and within specification. Some other work we've done is the work on the top right here is actually looking at layer thickness, which was not something people look at very often. see people talk about. They talk about the laser and velocity and power and beam size and shape and all this, but we've actually found that the layer thickness has a very large impact on the material properties and also the reliability of the part. So this is an area where we were just measuring basically the motion of the stages, right? As we see quite a bit of variability here, which is sort of in the range of what we kind of think would be acceptable, and it seems to work quite well. But this is an area where we actually need to do a little more work. But this is something that you have to characterize. The bottom right is actually, so we did this work with the thermal lensing problem. We actually upgraded our lens with the vendor, and this all went away. So this created a bunch of challenges. We've resolved those now, and so now we have a machine that's very robust. We're printing samples, daily with a lot of reliability and trust in what we're getting off the machine. One of the things we did is I had a student that was working on process structure maps. So one of the things in addition to understanding the powder and understanding the machine, we wanted to understand the process space. And so we did a very extensive study for over about a year and a half of looking at all the different metrics on the machine itself and how it performs. We did a bunch of different experiments. Some of this is a little bit of a brute force exercise, but it's been very helpful to us to understand the process and how to approach a machine and understand what it's capable of doing. In this space, a lot of people talk about process optimization. I tend not to use that term anymore because I don't believe anybody's optimized for hardly anything. They may optimize for a parameter they think, but other things are impacting that, and I'll show you that here in a second. First thing, we started off with simple line scans. These are actually super easy to do. The challenge here is actually a characterization. This scan is actually just lines on a solid plate or on a buildup of powder, or what we call a pad. The run itself takes a few seconds, right? You hit go and you blink and it's over. But what we do is we cut these up and characterize these. They give us a really good indication of process settings, of melt pool conditions, of depth and width, whether we're getting lack of fusion or balling or keyholing or stuff like that. So these are really, really effective. And actually, we were able to, I have this slide. Yeah, so here's some results. You can see some of this where we're doing on the plate again. So there's no powder on this. It's actually super simple. It's easy to do. You don't even have to have your machine necessarily. If you have a laser scanner that's similar, you wouldn't even have to do this on a machine, but you can capture sort of these keyhole events or, a good, nice melt pool or something where you get balling where you're not going to get good material adhesion. We then can also translate that and do that on a pad, a little more work, not a lot, and we can do the same sort of thing. And so you'll see the trends are slightly different, but these are great starting points. I don't believe I have the slide yet. I don't have the slide. So one of the things we did here was we took a very simple model and fit to this. And so we have the ability to take both experimental data and even do some model fitting to do some prediction. It says, hey, if I have a layer thickness of 30 microns, what's my melt pool depth that I want, right? What does it needs to be my hatch spacing to create dense material? We can do those predictions. We also did a large work in looking at density cubes. So there's a range of things we looked at here. Density is a metric that almost everybody uses, but it's not the end-all say-all, and I'll show you that here in a second. We also looked at surface finish, and you can see a whole range of finishes on these parts. We also looked at microstructure, and I'll show you some of the results there, because there's a wide space here in which the process will actually work. So here's actually some results from that. So these are, looking at the vertical axis is the laser power, the horizontal axis is the scan velocity, the circles are all areas where we run parts. The open circles are parts that failed in this space, and then the closed circles are parts where we actually were able to print cubes. And so you'll see in some spaces we actually have some surface finish data, which is related to the fact that we built a little bit, but not enough for, say, a density measurement. So you'll see a range, high density is up here in the top, but if you look at the other metrics around surface finish on the top or on the side, or even sort of form, so this would be, say, the waviness or the flatness of the top surface, just because I get good density doesn't mean I necessarily get good surface finish, right? So when we start thinking about process optimization, it really needs to be multiple factors, multiple constraints in terms of what you're looking for, right? And so that's a key piece that a lot of people don't look at. If you look at this X on this image, this is actually our nominal settings for our machine itself. Turns out when we look at all this data, whether the vendor, I don't know how the vendor got to this point, but the point that they've given us is actually reasonably good for creating both parts that have good material properties, good surface finish, and reasonably good form accuracy, right? And so I don't know how they converge to that point, but it's sort of interesting that our settings are sort of somewhere in a place where you would want to be. Again, it's it may not be to say the minimum surface finish, but it gives you a good constraint of all those types of metrics. Here's the thing we see that with the microstructure, one of the things that's interesting in this space, so everybody gets it around the topic of material properties, and you see a lot of variation in these machines, and there's been lots of wailing and gnashing of teeth and why this is a problem and all these things. This is part of the challenge. This is part of the reason why. These are all cubes that built just fine. Some of these are actually quite good density, but the microstructures are quite different. And so this is going to change the properties. We'll see this in a second. So now you have to think about, okay, what's acceptable? What do I need? What can I work in? But you really need to have this kind of data and have this understanding of the process to really say, yeah, it's working, it's doing what it needs to do. It really turns out you have a wider process space, at least in powder bed fusion, than a lot of people sometimes think. Let's see. Oh yeah. So this is actually showing. So this is the settings, 120 watts. This actually shows what happens if you just change the powder layer 10 microns, right? So sorry, went the wrong way. Yeah. So this is 30 micron, 10 micron change, and you see a dramatic increase in porosity and the reduction in the microstructure, right? The grain size. So these are all things a lot of people don't always think about, layer thickness. They just think it's 30 microns. Well, it's not really. It's a variation, right? So these are all things that probably introduce a lot of the variability we see in the processes in some cases. So a lot of the data you're seeing here is actually our Gen 2 high throughput tensile tester. This was when we started the Gen 1 work, we realized it worked extremely well, but we found that a bottleneck was actually the fact that we had to have somebody, a technician or even a student, loading samples by hand, every minute or two. So actually what we did was we went in and we changed it. We added a linear axis to our load frame. And so now we're using DIC from the side, not the front. And we're automating. So now we can put, I believe this will hold 50 or 75 tensile bars. And so now we can load up a frame and technician can walk away from it for an hour, right? And so now we can start loading things at a much faster rate. We use this quite frequently. In the 4 years that this system has been up and running, we've printed probably and tested multiple thousands of tensile arrays. And so we got a lot of data here, right? So you can see sort of the what we need. And one thing that's nice about the samples, we can get up things besides tensile properties. We get density, we get surface finish, all those things off in the system. So when we take this and go back to our process map, one of the things we find is an understanding of where our properties lie in this material. These are, again, tensile properties. So we're looking at modulus, we're looking at ductility, we look at yield strength and ultimate strength. And you'll see really the thing in here, you see again the axis where are our nominal settings. This is shifted a little bit from the previous plot because we don't print the tensile bars in quite as wide a process space as we do in the other ones. But you see a range of properties, change in ductility, which sort of matches things like Hall-Fetch relationships, where we have an increase in ductility with increasing grain size, right? So you see that trend. So depending on where you want to be, we actually did some work where we were getting a ductility a little bit lower than we wanted the nominal. We showed that, well, if we increase or change our settings, we can actually increase the ductility of this material, maybe at a reduction of yield strength, but it was acceptable for that application. So really what this gives you is another design knob that says, hey, I can take my process or I can take my geometry and now, again, tune the complexity of my part, right? So in some ways, this is really exciting to the process folks and even possibly to the designer, but it gives you another level of control that may be useful. And so here's actually data, taking all these pieces, the powder, the machine, the process, the settings, understanding those types of things, understanding porosity defects. This is actually sort of a similar scale to the slide I showed earlier with 1,000 dog bones. It's not 1,000 dog bones, it's more like 600, but this is data over about a year and a half, 2 years on our machine with an upgrade in the optics and also changes in powder. And you can see a much better, much tighter distribution on what we're getting in terms of properties, right? Still a spread, still a variation, but the distribution is much tighter. We have much more reliable control of what's going on. And so we can use this information to inform a lot of things on the design side. Real quick, I'll wrap up. I think I'm running out of time here, but looking at some of the work we're also doing. And so I talked earlier about the fact that what we found is that large defects are a problem. How do we identify these? And this is work we've been doing, which is a lot of fun. Looking at real-time monitoring. So there's on the left, there's actually an image showing tracking the galvo motion of the laser itself. And you actually see here in the bottom left, there's actually deviation. So this is what it's supposed to be doing. and we see actually a millimeter of travel variation. This was sort of a test run, just checking some stuff with the galvos, and we saw this error, which was very unexpected, right? And so this could potentially be an impact for a defect. We've also done a lot of work looking at melt pool monitoring, looking at pyrometry and the melt pool signatures. And there's a lot going on here, right? So this is a really dynamic process. A lot of things are happening. And it's amazing that we actually create good material sometimes when you look at these images. But we did a bunch of CT data inspection of these parts, looked at the pyrometry data, and have done some things like machine learning with some clustering algorithms to actually show that we can predict, we find these outliers in these melt pools that correlate typically with spatter events. So basically, sort of upset where you have molten particles flying out of the melt pool. We start correlating these, and we can identify these large porosity voids in the structure, right? And so this gives us the ability to find porosity. We've also shown that when we use this pyrometry data, we can find deformation defects in the part, right? So this is pretty obvious when this comes off the machine that this part failed here on the bottom left. But really what you could do is you can start monitoring these, and you can say, hey, I've got a problem. I need to correct something. I may have to stop the build or maybe change the build or whatever. So it shows you at least a path forward to doing possibly either local or even global process control on your machine to improve the performance of the material and what's happening. Real quickly, again, addressing the complexity piece, there's a lot that has to be done in terms of data management, and actually Aaron Wong has been working with our group this summer, has been working in this space, looking at actually taking micro CT data from lattices, some complex geometries. But there's a lot of things that are required to try to take these data sets and do analysis, right? There's not a one-stop shop tool at this point, although this is a little bit dated, some of these are consolidated, but there's a lot to be done here in managing the data. And I think my last slide is basically talking about that, right? So we have a lot of fun with a lot of the processes and the materials and doing the testing and the characterization. But one of the things I've learned in the 3 or 4 or 5 years in a lot of this work is that the data is becoming a huge problem and a need and a challenge and a point of emphasis. And so a lot of the work we've been doing is trying to figure out how do we manage the data from the build, from the process. We have process sensors. What do we do with all that data? It becomes a big data problem pretty quickly. And so there's a lot of space here in additive to really address a number of research and R&D topics for students, for professors, for people at the labs and stuff like that, right? And so these are all things that we're looking at and trying to deal with this complexity. I believe with that, I'll stop and see if there's any questions.
Thank you very much, Bradley. So the floor is open for questions. Right now, there's only 7 of us here on the call. So if you have a question, please just go ahead and unmute yourself and ask.
Hello. Thank you, Dr. Jared, for your presentation. My name is Christopher Wheatley. I'm an REU student at the University of Kentucky. And I was interested in going back to, you mentioned that there was some variability with depending on the layer of the material. I was wondering if that was more related to the temperature differences, like if a higher layer would have more thermal heat from cooling, or what kind of temperature relationship that could be with those layer variabilities.
Yeah, that's a great question. And actually, if you look at the data, there's a bit of a measurement uncertainty, and part of this is one of the challenges with this data set. But yeah, you start thinking about the layer thickness, and it becomes a challenge. And there's a couple ways. One is the machine itself. The other is the fact that you're putting down powder and you actually don't have a consistent layer, right? So now you start thinking about, hey, if I have powder particles that are deeper, how does that impact the variation in terms of the laser process? And if I have a thicker region, is that going to melt and solidify? So yeah, you absolutely. So now you have to think about, well, now I have to make sure I have enough heat to melt that, right? So if those deviations are large enough, you could actually have inadequate melting. And so it's actually an area where there's not been a whole lot of research. We've got some experimental data. Haven't really explored this probably like we should have. But I think it's actually a topic that's probably not been appreciated, and people don't really talk about it much. But I think it's actually one that could be a source of a lot of variability in some of these processes. Typically, with the settings on the machines, we're typically melting a couple of layers with the melt pool itself. But even then, there's certainly an opportunity to have deviations and have issues with that, right? So if you And like to your point around the temperature profile, if I have a deeper powder, powder has a different thermal conductivity than the solidified material, right? So the conductivity is lower. So you actually retain more heat in powder than you will in a solid material. So it absolutely changes the boundary conditions of the process, which again, I don't think anybody's really characterized. We thought about it a little bit, but it's a good research topic. Good question.
I had another question, I guess really directed more towards you. As transferring from a national lab to a professorship at a university, I was interested in what you thought of, I guess, what has been your experience with national labs, and where do they fit in the academia surface, in relation to universities or industry or other agencies?
Yeah, so I've actually, of course, I went to grad school. I actually spent the first 8 years of my career in industry working for 3M and Corning, and then I spent the last 13, almost 13 here at Sandia. The lab's a great place to work with a lot of fun. I'm actually from Tennessee, so going back to university is going home for me a little bit. So there's a piece of, there's not too many jobs I would take to leave Sandia, to be honest, and that's one of them. So the labs are a lot of fun. You get a lot of really interesting problems. Sandia, I'll speak to Sandia because that's where I've worked. I've worked with others, but at Sandia, there's a lot of flexibility. There's a lot of interesting topics, a lot of things we do here. Weapon systems, a lot of people know about that, but there's a lot of things in, energy, climate, cyber, a lot of stuff we're doing on the process side of material science. So you have, at the labs, you have sort of a little bit of the best of both worlds to some extent. It depends on where you want to be and what you want to do, right? If you want a job where somebody tells you what to do, we have those jobs here. If you want to be sort of an academic where you're going out doing research and writing proposals, that can happen as well. So the lab systems are actually really nice. I'm a big fan of the labs, and I hope to continue collaborating with them. But in terms of a place to look for an aspiring graduate student or an undergraduate student, a lab, if you have an opportunity, it's a great place to work. And so I would definitely take that opportunity if you've been given it. Again, you get a lot of flexibility. You get to work with state-of-the-art equipment, and many times there's challenges, but there's challenges everywhere you work, right? But yeah, the labs are a great place.
Thank you very much, and thank you for the presentation. The animations were fantastic.
Well, thank you very much. Appreciate it.
Can I ask a question?
Absolutely.
Hi, this is Raimundo Arroyo from Texas A&M. In your results where you show the dramatic decrease in variability in the mechanical performance of the AM parts, so was this the outcome of finding the sweet spot in the process window, in the process space that minimized the likelihood of having, all kinds of potential defects such as keyholing or lack of fusion or other, types of?
A great question. Yes, to an extent, yes. So if you go back to the 17.4 data, there's multiple things. I didn't go through all the details. There's several things. Some of these are inherent. So 17.4 is actually a much more difficult material to process. It's much more sensitive to process variations. 316 stainless or 304 stainless, 300 series stainless is actually quite robust. NDU uses it a lot for that very reason, for other things. So the material itself is actually more robust and less sensitive to process defects. That's one thing. The other thing is we did do the work to characterize our machine, and we eliminated a lot of the variability and the challenges. After the fact, we learned on the 17.4 material that, for example, that the material that was printed on multiple machines, potentially with multiple different settings. And so there was all kinds of variation that was occurring there, right? And so, again, the piece here is to understand your machine and to know where your settings are. To some extent, the process maps that I showed you really aren't necessarily important here. They could be if you want to change your setting and you want to change your set point, say, hey, I want different properties. I want to guarantee different, elongation to failure, different, yield strength. You can do that. But what you really want to be able to do is say, okay, I know what I need. Now I know how to set that and basically know where to make sure that it's in that regime, right? So I know my machine is stable. I know what my machine is doing. I think that's a big key to addressing that. These additive materials, certainly in powder-based processes, have a level of variability that is really difficult to get out. And we found that actually this variability within reason doesn't change a whole lot across process settings. At some point, you do cross a sort of a threshold, and it does change a lot. Things like HIP, hot isostatic processing, where you basically heat treat the material with both temperature and high pressure, can produce better material in some alloys, and some alloys it doesn't help as much. And so those are all things that people look at as well. So again, there's a lot of things that happen in the complexity piece. But the fact that we understand our powder, we understand our machine, we have control over the set points of the machine, and we're not changing those things, has really been the big key in terms of managing and keeping reducing that variability.
No, I have a follow up on this because, my understanding is that if you find yourself in a region in the process space where, it's more likely to have some type of defect like porosity, right?
Yep.
Then, the material, would act like any other material that is limited by, the statistical, distribution of defects. Like, in a ceramic, you have a lot of variability because ultimately fracture strength is going to be controlled by the population of defects that you have, right? And in a additive manufactured metal part, under tension, if you are in a region of the process space where it's more likely to have porosity of different kinds, it's probably more likely that you're going to have a distribution of performance, because the distribution is not going to be controlled by the intrinsic properties of the material, but by a particular instance of defect populations in that material.
Absolutely. So if you look at this, hopefully you can see my slide here. So if you look at, say, the left 3 or maybe 4 images on this plot, these are all different set points on the machine where we're getting different grain structure. We're getting basically fully dense material, right? Again, there's sort of an inherent porosity in some of this that it's really difficult to get all of it out. But this is what I would consider good material. So in those sort of, say, 6 to 7 or 8 images, microstructure set points, we're going to get a distribution that's going to have probably the same span or width, but the averages are going to be different, right? We're going to have higher ductility in one or higher yield strength in another, right? So that's going to be a distribution that's going to look very similar in both in terms of size and shape. When we start looking at the far right side of these, where we're seeing these porosity defects, you're absolutely right. So that's going to be an area where we are going to see larger variation because we have these porosity and void defects in what's happening. And so, yeah, you want to make sure you're not on the right side of this plot, and you want to make sure you're on the left side. So if you're on the left side of this, again, you're going to get fully dense. But this is why I said, density is not necessarily the best indicator of goodness of the process. It may be good enough, but it may not really be where you want it to be necessarily. This is where, vendor A and vendor B can sell me material, and it's really good dense material, but I have different material properties. Everybody wrings their hands, and they go, well, what's going on? Well, it's because the microstructure is different, right? You have process conditions that are different. Either the beam diameter is different, or the power setting is different, or both are different. And so these are all things that you have to consider. And you got to look at that, right? And so I had another thought. I lost it. But yeah, to your point, as long as you're in this sort of fully dense region, your distribution should look fairly similar. Now, again, where's the average or the mean? It's going to be different. But you should have a part that you could claim reliability around in this space. Oh, I know what it was. The other thing is a lot of the distribution is actually going back to the surface effect. From what we've seen, internal voids, until they become really large, and on the right side of here, you see some large ones. Most of the failure we've seen in these parts, if we don't have large voids on the inside, most of it is actually at the surface. And so the surface finish is actually critically important. I don't have a slide here. I've got some results that show if you take off the surface, you machine it or polish it or whatever, you can get much better effective properties, right? So it's not really the bulk property you're changing the structural property of the material, of the member of the part. The bulk properties are still what they are. And so those are all things you have to consider. So surface finish can be as big a driver as process settings in some of these types of things.
Thank you.
All right. Well, thank you all for the great questions. And thank you, Bradley, again, for this wonderful overview of additive manufacturing at Sandia. We wish you all the best at Tennessee.
Thank you very much. Appreciate it. I thank you for the opportunity and appreciate your time.
And I would like to remind everybody to join us next week for our last O-REU seminar with Professor Raimundo Arriabe. Have a great week.